Hello everyone, welcome back to Advent of Code 2025. I'm going to do day 10 today. I wanted to talk a little bit about day 9 yesterday, which took me like forever. And I said near the end I was interested in seeing how other people did it that was more efficient than mine. Because mine clearly ran too slowly to be what Eric expected us to do. I was kind of disappointed to find that mostly what people did was take advantage of the input not having all the difficult cases that I was trying to work around. Right, I envisioned, for example, what if what if there were like a red cell here that dipped down to another red cell here that dipped up? Then this whole area is green and is valid for being part of a rectangle, but it doesn't necessarily look like it because there's an edge here. But both sides of that edge are actually in the polygon, so it's fine, right? So I actually, spent a lot of time coming up with an algorithm and implementing it to actually address that. And there were some comments on the Haskell subreddit that referred to the Advent of Code subreddit that had example inputs that did have these properties that nobody's actual inputs have. And my solution does work for those. So I solved the hard version. But you didn't have to solve the hard version to win yesterday's problem. So it's a little bit disappointing. You could think of it as wasted effort. I don't. Right? In some sense, this is all wasted effort. Someday I'm going to die, and, having worked on Advent of Code before then will not matter anymore. And even in a somewhat less morbid sense, I'm just doing this because I want to do it. I don't think it was wasted to have, to think up a solution to a more difficult algorithm problem than, quote, necessary. Because it was the problem that the problem statement described. The input just didn't have the fully general. It didn't cover all the corner cases that the problem specification allowed for, and I wrote a solution that addresses all those corner cases even though they weren't there. So I don't think that's a waste. It was an interesting way to spend time. I'm disappointed not everybody else had to do it, but that's life. Let's move on today to day 10, factory. Just across the hall, you find a large factory. Fortunately, the elves here have plenty of time to decorate. Unfortunately, it's because the factory machines are all offline, and none of the elves can figure out the initialization procedure. The elves do have the manual for the machines, but the section detailing the initialization procedure was eaten by a Shiba Inu. All that remains of the manual are some indicator light diagrams, button wiring schematics, and joltage requirements for each machine. For example, and then some gobbledygook that we will learn to understand later. The manual, right, these are pieces of the manual, describes one machine per line. Each line contains a single indicator light diagram in square brackets. Okay, presumably hashes are on and dots are off. One or more button wiring schematics in parentheses. And joltage requirements in curly braces. They've got all three of these, huh? Okay, sure. To start a machine, its indicator lights must match. Oh, is this like a lights out puzzle kind of thing? Its indicator lights must match those shown in the diagram, where dot is off and hash is on. The machine has the number of indicator lights shown, but its indicator lights are all initially off. So an indicator light diagram like this has 4 lights, and your goal is to get the second and third on only. Yep. You can toggle the state of indicator lights by pushing any of the listed buttons. Each button lists which indicator light toggles, where 0 is the first, and so on. Yeah. When you push a button, each listed indicator light turns either on if it was off or off if it was on. You have to push each button an integer number of times. You can't half press a button, nor negatively press a button. So button wiring schematic, okay, each time you... Yeah, I understand. Because none of the machines are running, the jolt requirements are irrelevant and can be ignored. Okay, that's sort of a hint to what's going on in part 2, I guess. You can push each button as many times as you like. However, you'll need to determine the fewest total presses required to correctly configure all indicator lights for all machines in your list. So you could push the first 3 buttons once each, leaving 3 alone, toggling 1 and 2. Yeah, that makes sense. Or you could toggle 3 twice, 1 and 2 once each, and then 0, 1 twice? Wait, that doesn't do anything, does it? Am I stupid? Doesn't pressing 0, 1 twice just... Doesn't pressing any button twice have no effect? Yeah. Right? Oh, okay. And then they say here that you can do it with 2. I was looking at these as like the examples that are, oh, okay, yeah, but pressing just this should also solve it, right? Because pressing anything twice is a no-op. If we pressed 1 and 3 once and 2 and 3 once, then 3 would stay off and 1 and 2 would turn on. Yeah, that's right. Okay. This is like... There's got to be some well-known kind of Boolean logic constraint satisfaction thing going on here. This could be the day that I learn how to use what do you call those things, like sat solvers. I think it would be overkill for this, but it would maybe be an interesting thing to learn. I'm sure there's a simpler approach, but I don't know what it is. Like, a sat solver is a very general tool, right? So, like... We could, for example, like if I were trying to solve this kind of thing by hand, which I've done before. There are puzzles where you have to do something like this. In the it's How to Escape Submarine Simulator. There was a game like this that I played. That's on the channel if you're interested. Where you had like a maze that you had to make solvable. But you could only do it by toggling switches, and each switch turned some wall sections on and some wall sections off. And like, so I started by charting out, like, okay, first of all, which wall sections are affected by each switch, because that wasn't obvious, but that's given here. And then like, okay, well, I need wall section 2 to be on. And so that means... like, of all the switches that affect section 2, I must press them an odd number of times in total. Right? And we can do that here. Like, which ones affect 1? 1, 3, and 0, 1. So between those two groups, we must have an odd number of presses. And sometimes... you can immediately solve something from that. Are there any examples of that here? Yeah, like we can see... well, no, not quite. Because all of these are touched by at least 2 switches, right? There's 3 that touch 3, 2 that touch 1, 2 that touch 0, and 3 that touch 2. So there's no button that you can immediately rule out just like... because nothing should ever touch it, right? Here though, there is one you could immediately rule out. 5? Oh yeah, I just can't count. I thought there were only 5 here. So 5 is the 6th one, which is this. So on this one, you can say for sure you must press this button exactly once. And that would kind of invert how many times you must press all the other buttons. Or all of, you know... You would then change it. You would say, okay, I'm pressing this once, and my new goal is for this to be pressed an odd number of times instead of an even number of times from the remaining buttons. Because I pressed it once. And so my goal was to have it pressed an even number of times. I've now pressed an odd number of times, and you press it an odd number of times again. So this one you could immediately like say, I'm done with this, solved. But most of them, like this one, I don't know, do I press this? It kind of depends on whether I've pressed this one and this one, right? Interesting that this one and this one don't overlap at all. So, there's... Okay, let's look at the input before I get too deep into thinking about how to solve this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 buttons in the first one. So that's about how many buttons we can expect, probably, for most of these. You know, this one only has 4... This one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 seems to be about the cap. We're not going to have 100 on any of these. And so, like, there's one obvious algorithm, which is just guess, right? There's only 10 buttons, and each one is pressed either 0 times or 1 time. So you can, you know, in 2 to the n steps, just try all of those and see if any of them give you the light up pattern that you want. We have 150 machines and 2 to the 10th, which is 1,000 possible sequences we could try for each. That would certainly be fast enough, right? I think that's true. It would be more fun to write something a little bit smarter. Which, I guess, I mean, I don't know. Maybe there's some way you can solve this totally analytically with no backtracking. But it's not totally obvious to me what it would be, right? I said, okay, yeah, in this one you can conclude that you have to press this button once because it's the only way to toggle light 5. But then, like, the other 5... I mean, you could figure it out, probably, right? You then have to press these an even number of times in total. No, yeah. Because light 3, this one, needs to be on, but sorry, an odd number of times needs to be on, but wasn't toggled on by this. And pressing these both is the same as pressing just this, right? Because it flips 0, 3, and 4 twice, and 1 and 2 only once. So if I'm flipping these an odd... Oh wait, well that's not helpful. Maybe? So what do I still have to turn on if I've done this? I have to turn 0 off. And 3 on and 4 off. So I think it would just be this one, right? So we could solve that kind of by hand. But it requires some sort of complicated analysis in a way that I would have trouble encoding properly. Whereas just backtracking is quite simple. And you can speed this process up in some ways. Like, well, the backtracking algorithm, let's say you just started with this one and guessed, oh, it'll be off. Guessed this will be off, and keep going until you're done, and then see, oh, okay. Well, I didn't solve the problem, so one of them must be on. Let's try turning this one on. Something like that, right? And actually with mapm in Haskell, it's actually quite easy to get like the power set of a list of booleans, for example. Or I guess it would be replicate m in this case. Anyway, it doesn't matter. But like, you could be smarter. You could say, okay, I have 4 buttons to think about, and and each of these light goals creates a constraint on a set of buttons, right? This 0th light being off constrains these 3 to be pressed a total number of times that is even. Oh my god. I accidentally clicked OBS's start streaming button. Does it still have my broadcast key? It probably does. I hit stop streaming immediately, so I don't know. On YouTube, that won't do anything. But I think it is set up with my Twitch credentials, so I may have created a stream that was 2 seconds long or something. Anyway, so there's the constraint on these 3 created by this light. This light creates a constraint on all of them but this. This light creates a constraint on this one, all of them but this again. This one creates a constraint on the first 2. This one creates a constraint on the first 3. And this one creates a constraint on only the third one. So we could start by analyzing the lights and the buttons to determine a set of constraints. Or like, for each light, a set of buttons and their constraint. And so we'd have a set of constraints equal in size to the number of lights. And then, rather than just blindly backtracking, we pick one of the buttons from among those with the fewest constraints, or the smallest set of buttons involved in their constraint. the set of, I can't quite word this. We choose a light to try to satisfy from among the lights that are connected to the fewest buttons, basically. And in some cases, that'll be 1. Like in this one, we would say, oh, well, light 5 is tied to just 1 button. So let's just mark that one solved. But maybe in some other cases, like this one, you know, light... They're all... Well, light 1 is tied to 2 buttons. So we can't be perfect, but we can, you know, guess one of these, and that will force the other one on the next step, right? And at each of these steps, shrink all the constraint sets accordingly, right? Or edit them accordingly. And that would give us a faster search method. I think I'm not going to do that, though. It's interesting to think about, but it doesn't seem necessary for part 1, and I have no idea what part 2 is going to be. Joltage requirements. What could that be? I mean, I noticed the number of joltage requirements are equal to the number of lights, not the number of buttons. I don't know. But let's just do a simple backtracking search. And we won't even have to do any of the backtracking by hand. It'll just happen through the magic of functional programming. So let's see. This time, TextReg Explicative is a great tool because the input file is composed of several different pieces. Writing one regex that handles all of this would be quite complicated with a PCRE style approach, because you have to, like, oh, match this, and then find each of the places where this matches, and then match this, and then, like, parse each of those separately. What a nuisance. Instead, I'll just write a big old function. Which, you know, you might like more or less depending on your views, I guess. I want the match operator, sum, man, YouTube Music is playing me some weird shit. I mean, I'm sure it's lovely music, but it's not the kind of thing I would listen to by choice. It just is like what you get if it falls off the end of your music playlist. It just gets weirder and weirder until you finally correct it. Okay. So we want to match sum. We need symbols. These are the main tools I always need for TextReg Explicative. What else is in the input file? I mean, not much, right? Yeah. All I really need then is a parser for ints. And then I need a bunch of types. Data machine. Is it a machine or is it a diagram of the machine, a schematic of the machine? We'll say it's a machine. It's a machine containing light goal? I mean, do I want to type for that as well? Probably. It could just be a list of bool, but well, I mean, why not? I don't think we're going to get anything fancy, useful out of defining a new type for it. A list of bool, and then a list of button. And this I do want to be its own type. And then a list of joltage, where type joltage is just an int. And do I want a new type? Why exactly? I could just make this a type alias as well. Yeah, I probably should. A button is just a list of int, I guess. I mean, it would be nice to specify that these are distinct, wouldn't it? Like, I can create invalid buttons with this specification by saying the button toggles light 2, 2, and 2. Also, I guess I'm going to want to do membership operations on this, so a set sort of makes sense, right? Okay, we'll use an inset. And I can still create invalid buttons by using negative numbers, but at least there won't be any duplicates in them. So my input is a list of machine using this specification. Let me just make sure that this much all compiles. I haven't messed something up. Okay, good. The import of sum and sim from text explicative is redundant? What do you mean? I understand sum. Sorry, I understand. Yeah, sum is like from applicative or whatever. What do you mean? Oh, it's redundant because I'm not using it. Sure. Not because it's already in scope. So an input is a machine mapped over some machine followed by new line. Simple enough. Not quite. So some, oh, I guess I should just do this. It's some machines, each followed by an empty line, and then each of those will fmap machine in, of course. Machine is machine of, I guess it's pretty simple, right? We say lights. How do I handle the spaces? I think I'll have each thing I parse be responsible for the space after it. Some button. And then voltages, I guess. Lights is an open pair, no, an open square. Ignored. And then some light. And then a closed square. I think that's all, right? Yeah, I already handled the space. Looks good. Joltages is going to be similar, so I'll do that nearby. Joltages is sim curly. And then decimal set by sim comma, and then close curly, right? Yeah. And a button, a single button, is well, I guess I should just repeat I should factor this out, right? List ints of before and after, let's say open close, is sim open, sim close. So jolters then is just ints open curly close curly, and a button is ints open paren close paren. So this is another reason I like text vector explicative, right? It's all just functions and ordinary values. You can factor out duplication whenever you want. So this sort of looks right to me. I don't have a proof yet. Let's try prepare. Doesn't even parse. Right, I haven't written set by, of course. Set by p set by sep is, let's write it correctly this time. It's cons f mapped over p, and then, oh, I need many, don't I? Yes, that's true. Many sep and then p. Right? I haven't defined light? That's true, I haven't. You're right. Light is true if you are able to parse parents, please. Hash or false if you are able to parse a dot. God, I'm always amazed this is not in the prelude these days. Close. Oh, it's an int set. From list needs an uppercase L. Yes, and you have a suggested fix there that I didn't read, but it is what you should have suggested. Okay, a bunch more mistakes. Oh, the lights aren't insets. They're, what am I doing? I put this in the wrong place. It should be the buttons that are... How about that? A machine with lights some buttons that you've turned into... Do I not have enough close parens? No, I do. Oh, each button should be from listed. Should not not the list of... No, wait. Yeah. Good. Yes, I didn't give it a show instance. Very funny. And it parses. Great. Looks... I mean, that's the thing. One nice thing of TextReg explicative is, since it parses the whole file, if you get a value back, you know you, like... You don't know you didn't make any mistakes. But you know you did something with every character. So the kinds of mistakes you could make are much more limited than if you wrote a bad regex in a PCRE-style engine. Or bad code for parsing those regexes because it inevitably gives you back strings and you didn't want strings. So I think this is probably correct. It is a correct parser. But in case it's not, let's double check. So what's the first one? I don't have good setup for like splitting my tmux windows. I think I could do it with like Control-Z% to split them. I don't remember if that's vertical or horizontal split, and I don't know how to close the split, so I'm not going to do it. We're just going to say what? Well, I guess what I'll do is the following. I'll go grab the first of these and just, yeah, it's not how you copy. Let's just copy this much, I guess. Okay. False, 5 trues, 2 falses, 2 trues. It parsed the light diagram correctly. And that's 0, 1, 3, 4, 5, 6, 8, 9. 0, 1, 3, 4, 5, 6, 8, 9. That looks good. That's the first one. And the last one, well, we don't have. And the jolts is like 56, 49, something. Yeah, this looks right. And we can just confirm it got all of them, 156. That's how many there are. Great. Looks good. Commit this? Why not? All right, part 1. What are they even asking me to do? I know we're supposed to, for each one, like turn on the machine, but then what's the answer they want? Okay, the sum of the fewest button presses necessary to configure the lights on all the machines. So for each machine, find all the solutions, find the smallest such, and return that. I guess, I mean, it certainly is possible that the input could contain machines that are impossible to satisfy. But the problem statement doesn't tell us what to do if that happens, and so I assume it won't happen. Right, for example, we could have this machine, this light diagram, and no button that toggles light 4. You couldn't solve it, right? I'm going to assume that doesn't happen. My code will crash at runtime if that happens, and I think that's within, like, I went on yesterday about, or at the start of today, about how my solution for yesterday was great because it handled all the things that weren't actually in the problem input. But they were in the problem statement, right? From the problem statement, outlined a bunch of situations that could have occurred in your input, but actually didn't. And there was a correct way to handle those based on the problem statement. Here, the problem statement doesn't tell us what to do if there's a machine that can't be turned on. So I'm going to assume that never happens. So it returns an int. It's the sum of the map cheapest fewest presses. Maybe let's just say solve, because I don't know what's going to happen in part 2. So I'm just going to make a solve function be internal to part 1. Why not? Why not have it be global, and then maybe I'll just edit it in some small way to handle the joltages for part 2, and then I can reuse it. So let's map solutions. And I know, like, this is the same as mapping, writing this, right? I guess it's fine. Solutions. Well, okay, so I want solutions to return a list of all the buttons we had to press. So this is going to be the wrong, part 1 isn't quite right yet. It takes a machine and returns a list of bool. So now we have to say, like, call solutions, that'll make a list of list. Get the length of each of those lists and find the minimum. Or no, not a list of bool. List of int, the button indices we should press. I suppose it could return int set, but that does not seem necessary. So does this type check? Yes. Okay. So now we just have to write the solutions function. We've handled the overarching structure of, there's a list of machines, solve each of them and add the results up. And we've simplified down to just solve a simple machine, a single machine. Solutions of machine goal. Buttons. Joltages, which we will ignore. I think this will just be filter solved of replicate length. Well, filter solved, let's say button choices, where button choices is replicate length of buttons false true. So let me demonstrate. I'm gonna have to import this. Replicate I assume is still in control monad, even though it could be intraversable. Probably. list of int. Oh, my parentheses are wrong. Well, I guess that's fair. I said I wanted to return a list of int, the buttons that you've pressed. But it's more convenient in the implementation to return a list of bools, some of which are true and some of which are false. Well, okay, so let's say map like I want to make this presentable, right? Map make presentable. 2 ints in a weird way. 2 ints is a function that takes a list of bool and returns a list of int. And solved takes a list of bool and returns a single bool. Is this all type check? Oh yeah, that's true. Yes. This all type check. So I wanted to show you like a cute Haskell trick, right? Replicate 3 true, false. So this gives you the power set, all the ways you could choose true or false for 3 booleans. What is the type? Yeah, it is applicative. That's the type it should have. It was first defined with monad, right? Haskell had, in its early days, a lot more usage of monad, and applicative has gotten more popular. A weakening of monad that turns out to be useful in a lot of places. So that the names often refer to these older concepts. And they're even in older packages or modules. But anyway. Yeah, so I mean, replicate M is a very powerful... All the stuff that works in any monad is like unbelievably flexible. You can use it in so many different contexts. And for example, for lists, replicate M, says perform this monadic action n times and build a list of the results. And for lists, an action is choosing between these alternatives, a set of alternatives, in this case the alternative is true or false. And if we do that 3 times and make a list of the results, we get a list of the 8 ways you can choose 3 booleans. And you can implement replicate M. You can use it for doing I/O actions 3 times as well, right? Or it doesn't really make sense for maybe. It makes sense for parsing though. Like, a parser is applicative. If you can parse an int, replicate M3 is parse 3 ints. Although you would have to have some spacing between them so that they, whatever. So anyway, replicate M, cool tool. And for a list of booleans, it gives you back a list specifically of true false. It gives you back a list of all the ways to choose true or false for each of those, for that many different options. So let's do 2 ints first. It's sort of straightforward in a way, I guess. We want to zip with... The buttons are labeled 0, right? Yeah. The problem statement here since the first button is 0. So zip with 0, all of the bools. Then oh, did I write 2 dots? Filter second, and then map first, kind of, right? Yeah. And so we could say, oh, I mean, I guess it's I don't know, we don't really need to test this, it looks right. So solved is, of course, the interesting part. Although I do want to emphasize, this replicate M is doing all the backtracking for us. We don't have to do it anymore. We just generate all the possible ways you could guess N buttons, and then we check which of them are right. You know, if you were writing a backtracking solver or something, you know, you would have, that would be some logic you'd have to implement that we're not going to have to do. And if you just generate a list of all the ways you could solve, then you have to keep them all in memory at the same time, which isn't a big deal, I guess. But I think this all should fuse and stream, right? Haskell should be optimizing this to something more like a loop than generating lists of lists of lists, probably. I'm not going to try to find out because I don't want to be disillusioned, but that's what I choose to believe. Solved of... Actually... Let's see, what do I want to do with this? I guess having a list of bools is actually good here. It's more convenient than a list of ints, because I can zip that list of bools with the list of buttons. Right? I guess what I want is kind of to have an inset of the lights that are currently on, and then for each button that is pressed, toggle the things it corresponds to. Right, in a way? What does data.set give me? Or data inset, I guess. Loading up the old hackage docs here. Okay, an inset. Generalized insertion deletion, is that what I want? Yeah. Alter F. That's very general. Do I need something quite that general? How does this work? I've used Alter F and for maps and found it quite powerful to do something I don't need to do right now. How do I use it to do the simpler thing I want to do? Is there like an update or something? I guess there isn't because I don't have... Unlike maps, there's not a key and a value. You never need to update whether something is there. or if something is there, you never need to update its value. You just need to update whether it is there or not. All right, so let's try to understand Alt-F, because I'm sure it's powerful enough for what I want to do. Oh, right. Because I'm just returning a bool, I can just use identity here. The point of this f functor is to allow, like, let's say Alt-F just took a bool to bool that let you modify whether the thing is in the set. Then, with this function, you couldn't tell whether you had made a change. Your function would be called, and it would produce true or false, but it couldn't report any information to the outside world. You can't, like, because Haskell's purely functional, you can't, like, modify some flag variable that is in an outer scope and then check it. And so what the designer of this library has done is say, look, your function can return any functor that you want, and I will fmap into that functor to give you back the inset. And you can use this to smuggle information out in various ways. You can even do something crazy, like I have a bool function that returns IO of bool. I prompt the user saying, hey, the value is 5. Should that be in, or like the value 5 is currently in. Do you want it to stay in or be out? And the user enters a result, and then your bool function returns. And you would get an IO of inset that does that. You know, so you can do all kinds of crazy things if you're parametric over any functor. But just smuggling out a piece of information you can use as like, oh, I'll have f be either. And I'll return a left if some condition is met, and a right if I'm in like the normal state. And I've used that in past advent of code at some point. I don't remember what for. That's interesting. Let's go look, shall we? Well, I guess I don't need P. Yeah, there it is. Let's go have a look at this one real quick. So what was I doing here? I was altering the map with an insert. The function was insert of cycle num, so it knew what number cycle we were on, I guess. And I was inserting at the key state. No. Alter FKM. Yeah, the key is state. No, what? Shouldn't there be a value in there somewhere? Oh, of course. Alter F, the function insert, returns a value. Yes. So I called this insert function here. And if the key wasn't there, if it was nothing, then I returned a right and just n. And I said, yep, put n into the map. If the key was already there, there was a just in the map, then return left of p. There's no map at all. I'm just going to return p, the value, the key that was there before, that was already there, I guess. The key that already... No, I'm returning the value associated with the key that was already there. And then I pattern match here. It was a left. Oh, this is a state I've already seen before. When was it last seen? That's the left that was returned here. And otherwise, if I got a right of a map, then great, just keep going. So this was like some cycle detection thing. I don't know. Alter F is a very cool and powerful function. we are using it on sets instead of maps today, and we don't need its full power. But that's fine, I guess. So a machine is a list of bool, huh? I think I actually want an int set of bool, it turns out. Because I can always turn that into a list if I want, but it's nice to just say, like, these are the buttons that the lights that should be on. I'm gonna make that change. Lights, I guess, is... Oh, like that, excuse me. The other list of bools I have seems right. Does this still compile, or am I in the middle of something? Has inset bool. What are you upset about? Oh, it's an... Right. It's not an inset of bool, it's an inset. Just the ints that should... The light numbers that should be on. Sure. Oh, well then S instead of some light is not going to make any sense. Is it? Okay, I take it back. Just leave me a bunch of bools, please. Okay, good. So actually, this toInts function is more generally useful, isn't it? If I just say, like, this returns an int set, let's say. And I think length will still work because length is infoldable and int sets... Oh, int sets aren't foldable, aren't they? Because they're not parametric. Yeah, I'm actually going to have to use size. That's fine. Okay, this all still type checks with my changes to using int sets. And now that I have this function, it does make sense to make this take an int set, right? Because it's just so easy to call this in... Oh, buttons is actually a list. Yeah. It's easy here to say toInts of some lights, right? Yes, I need to... Like, I don't know. I just really hate having two imports here, like importing inset and then all the operations qualified. I kind of like just having one, but it is annoying to write S inset all over the place. fine. Now we're back to type checking and we actually have int sets in our machines now. Good. Okay, I've still made no progress on writing solved. But the neighborhood is nicer. So solved takes a list of bool. Solved is sort of equal goal fold L. Import that from data list. Press on the, not the list of buttons. Oh. Fold L won't actually work because it's, if I have an inset instead of a list of bool, which I want to have, so I actually don't want the fold L from data list. I want the one from intset. So we're gonna, on our list of bools, we're gonna two ints to get it into an int set of the buttons to be pressed. Then we're going to fold over those buttons, pressing each of them, starting with an empty set, and check whether the result is equal to the goal. That looks pretty good to me. Where, I guess this could just be, yeah, it's sort of nice for this to be in solved, not in where, in the outer where, because it is pretty internal to it. Press takes, let's see, fold L wants the accumulator, then the key, and the accumulator here is our list of lights that are on, and then a button and that should return a new set of lights that are on. And the annoying thing is this is also going to be a fold over the list of lights that that button affects. And I think this one is, well, I guess it's fine to have this, yeah. You could construct a set of lights to turn on and a set of lights to turn on and then do two set operations from that. But I don't think that's any better than just doing fold L over the list of lights, right? So give me back this, please. Fold L, toggle, starting with the set of lights that are on. the button. Yeah, and now this being part of an inner where seems kind of stupid, doesn't it? Maybe these should just both be outer, because we're not using anything from the inner closure. I think this is the more responsible thing to do. And toggle takes a light number and a set of lights, and it is run identity, which I'm going to have to import somewhere because I have to use a functor for something I don't even care about. Of S alter F. God, I'm going to want another function named toggle, aren't I? Invert, there you go. Alter F, so alter F's arguments. It wants a function, a key, and then an int. So, light, no, wait, the key is the int set. And invert of B is just identity of not B. Pretty simple function. I need control monad trans control. Is that where it would be? You would think so, right? Okay. Is it here? Yeah. Okay, my folds both appear to be backward in some way. Or maybe one of them is backward and it's leading to two errors. So a button, what is a button? It is an int set. It's not a list of int. Right. So this foldl here over the button should actually also be sfoldl, I think. Yeah, it didn't help. Well, it helped a little. The type error is a bit less wrong. Okay. I'm sure I just have the argument order wrong somewhere. So foldl takes a function, then a key, then a set, right? That's a little complicated because in one case my keys are sets, or my values are sets or something. So, okay. Well, something's wrong. I'm not ever looking at the buttons. Right? I should be referring to the buttons somewhere. That's maybe a hint to what's going on. So what is the button number? I'm being passed a list of bool, which I'm converting to a list of button indices. So I think I need something like this. Is that any better? No. Okay, let's put some types on these intermediate functions. That usually helps Haskell infer something more reasonable, because I'm having trouble processing these type errors as they are. But telling it what you meant for an internal thing helps. It gives you better inferences for when it's wrong. It tells you, it has a better idea of what to tell you was wrong. So press, I intend to be a function taking what? I guess an int set, I don't have to say S4 anymore, and then an int and a new int set, right? It's here's the lights that are on, here's a button number you should toggle, give me a new int set. Toggle takes an int and an int set and returns a new int set. And invert takes a bool and returns an identity of bool. Are these type errors any better? Now there's just one, and I think when I was writing down these types, it started to make sense to me, because toggle and press are both passed as arguments to foldl, but one of them, they take their arguments in different order, right? So one of them just has to be wrong. So toggle should probably just have its arguments flipped. Yes. Okay. I don't know. Let's try running it and see. It's a number. We like numbers. 436. We had 150 something, right? So this is like, on average, a little bit less than 3 buttons. That sounds plausible. It's the right answer. Great. Another instance of when your code finally compiles, it's just right, even though it's a mess. So we don't need foldl at all, after all. And I guess I'll leave these type signatures in there. I usually don't like them for internal definitions, but this is kind of messy, and it is nice to indicate what they're supposed to do, I guess. It's annoying to have to use identity, but for Alt or F, I mean, you gotta do what you gotta do, I guess. They could have provided something that's just alter, I guess, right? Which is like, there's only 4 possible functions from bool to bool. That you could pass to alter. So that's probably a reason not to do that. But I don't know, I mean, interesting. Alter F is perfectly fine. It's a great function. I don't need all of its power, but I do need... It's the only one powerful enough for what I need. All right, so what's going on with these joltages in part 2? All the machines are starting to come online. Now it's time to worry about the joltage requirements. Each machine needs to be configured to exactly the specified joltage levels to function properly. Below the buttons on each machine is a big lever that you can use to switch the buttons from configuring the indicator lights to increasing the joltage levels. Ignore the indicator light diagram. Okay. The machines each have a set of numeric counters tracking its joltage levels. What? One counter per joltage requirement. The counters are all initially set to be 0. Joltage requirement. The machine has 4 counters now, which are initially all 0. The goal is to simultaneously make the first one 3, the second 5, the third 4, and the fourth 7. Ooh. I see. Each button now indicates which counters it affects, where 0 is the first, 1 is the second, and so on. Yeah, so okay. Is there anything smarter you can do here than brute force search? Probably. Right? Like, you know, in this example, maybe, well, no. Yeah, here. Right? 5, this button is the only one that touches 5. So we can conclude that because light 5 must be juiced 5 times, you have to press this button 5 times exactly. Right? And then from there, you can probably figure something else out. What exactly is unclear? You have to press these buttons in combination exactly 5 times total because of light number 3. But these both touch number 0, which I guess is fine. It means 0 will hit 10. That's cool. Okay. So we can't just do this like try all the possibilities, because there's an infinite number of possibilities. But if we can produce plausible so, I mean, this is sort of a graph search problem, right? I think. And so was the last one. Sort of. But this one is more so. Turns out everything in computer science is just graphs. If you could produce a set of possible states, which would be an infinite list of all the states you could ever get to, sorted by how many button presses it took you to get there, you could keep exploring the first one and adding all the states it gets you to the set of pending states. And if you ever explore a state where all of the counters are correct, you declare victory. You say, well, that's how many button presses it took me to get there. Done. And if you ever encounter a state where any of the counters are above their goal number, you abandon that subset of the search, that subtree. You say, well, nothing I can do from here can ever get me to a solved problem, right? So just throw that away. Don't add its children to the search graph. So, I mean, this is kind of, I think, just a classic graph search. Like, I've implemented A-star, I've implemented Dijkstra, I've used libraries for A-star and Dijkstra. What do I want to do this time? Like, you don't need A-star, really, because you don't have a good heuristic function. I mean, I guess you could. Huh? That would be interesting, I suppose. What would be an interesting heuristic for this? The most obvious one would be... So, okay, A-star is a graph search algorithm that is most well known among, like, the I don't know, like, the general public doesn't know about A-star, right? Because they don't know anything about computer science. But, like, among computer science, it is most... I feel like it's most well known for use in games and searching two-dimensional spaces for, like, pathfinding. But that's not the only thing you can use it for, right? It can search any graph, and lots of search problems can be modeled as graphs. It's an extension of the Dijkstra algorithm to have a heuristic to try to explore more promising parts of the graph before less promising parts. Which means you need to give it a heuristic. How promising is the spot that I'm in? And the one constraint that it has is your heuristic must be what's called admissible. And a heuristic is admissible if it never overestimates the distance to the solution. You're always welcome to underestimate it, and if you always estimate that the distance is 0, then it degenerates into Dijkstra. But if you can get estimates that are greater than 0 and less than the actual distance, then you will have a search algorithm that explores things in a better order than Dijkstra does, where Dijkstra is basically just like breadth first or weight first, because both of these are applicable to search spaces where the edges don't all have the same cost. In our case, the cost is always 1. And I can think of one very simple admissible heuristic, which is that the distance from here to the solution is, at most, the difference, like the largest delta remaining on any of our joltages. Like, if our joltage goal for this is 5, or is 10, and we're at 5 now, we must have at least 5 more presses left. So we underestimate and say, oh, there's exactly 5. It's more than 0 and less than or equal to the actual number, therefore admissible and would direct A-star to search in an efficient manner. Is that really any, like, is it going to be more efficient in an amount that matters compared to just doing some dumb brute force thing? Because in a way, like, brute force would be kind of simpler, obviously. Because with A star, you have to like track how far you've gone, and on each branch, you have to know how far you've gone. And that might be different for all the nodes you're exploring, because one node maybe looks very promising, and you go down that like 5 steps before you even try anything else. And then you try something else, and like you have to know, okay, well, this is my first step here and my 6th step over there, and it's some overhead. Whereas since all of the steps are exactly weight 1, we could do this in a more breadth-first oriented approach, where we have a set of states, which will initialize to a singleton set containing all the lights are off. And then we just, for each state in the set, try pressing each button. And that'll give us a map or a new list of states we could be in, or a new set, I guess. And if any of those states are solved, we'll say, well, that's how many steps it took. The breadth I'm currently at, or the depth I'm currently at. And then, if not, for each step, each state that we are looking at, we will try each of the buttons. Well, first we'll evaluate, is the state illegal? Have we gone too far? Have we gone above the joltage requirement on any of the button, the joltage meters or whatever they're called? If so, prune that state. Otherwise, find that state's descendants, or immediate children, I guess, and add them to the list for exploration at the next step. I mean, honestly, I think that's fine. It'll be maybe a little bit less efficient than A star, but it seems way simpler. And I don't feel this year like going and finding an A star library. Like, I found one in a previous year, and it's fine. But this is simple enough that I think it would be more fun to do it myself. Maybe I'm wrong. And I already have one kind of cute idea for what to do at each step. We're going to have a list or set of states. I guess it should be a set, right? Because there might be 2 ways to get to, like, if you pressing button, like, let's find an example here. Pressing button 1 and then button 2, 1 and 2, is the same as pressing button 2 and then button 1. And we don't want to explore those states separately. We want a set. Okay, fine. So I have a, oh no, I'm going to want a set that isn't an int set. Disaster. I'm going to need 2 different data sets in scope. I'm going to have to, like, rename the other one as I or something. Anyway, where was I? Yes, I was saying, so we have a set of states we're in. And it's sort of, I first described it as, let's first see, are any of these solved? If so, report success. Otherwise, for, prune the dead states, the states that can never get to the goal, and then for the remaining states that still could lead to a solution, find the children of each, add them to the list, and then do the next generation. You can actually do that all, I think, with one operation, which would be like a fold LM, where we're folding over the set of states with a monadic effect for each step, which would be the ability to abort early with a result. That's what either or error or except or whatever does. It gives you a way to say, oh, actually, never mind all that. Here's the answer. So we could fold LM, and if we find a solved state, we return left and like the current depth. And then all the rest of the computation will halt. And if it's otherwise, we return right of a set of children, possibly empty if we're pruning this, and non-empty if we're not. Right? I think that seems like a pretty cool way to do it. Can we, like, unfold? Is that like a... What is unfold M? Like, does that exist? What would it even do? There's not, like, a super duper well... There's one in conduit, which I don't want to mess with. There's one in control monad free, which might be what I want. What does this even do? I don't know. It takes a B, which I guess is the seed. And a function that turns a B into an M of either an A or a traversable of B. Yeah, I'm not messing with this, man. Okay. I'll do that part myself. Okay, so I guess I need to... No module... Oh, I didn't change the import. Yes. Okay. Was that our number? It was close to that, right? 4 something? Yes, 436. Okay. I guess I'll put it here. So the solutions function, not going to need it after all, for part 2 at all. I'm going to do something. I thought it might be something that involved the joltages and the lights. Guess not. So it kind of makes sense to inline this to part 1. I guess I may as well. So where does this have to go? I need 6 spaces. I forget. Let's see. I think I can do this. Control 6, Control X, tab. Oh. I guess Control X tab does something different than I remember. I'll take it. It's nicer than having to count it for sure. Okay, does this all still... No, I messed up the indentation somewhere. Oh, this needed to be indented. Okay. So now I've moved that inside, and that's lovely, I'm sure. So part 2 returns an int, and it's kind of similar to part 1. It's sum of map solution in a way, right? Solution takes a machine and returns an int. And solution is where all the real work is going to have to happen. Solution of machine, and what do we have here? The int set, the lights we don't care about. Then we have a button and a list of buttons and a list of joltages. So, do I want to call go here, or do I want to run accept t? I mean, it's kind of weird to me that my plan is to have a computation that I expect to eventually return a left, right? What's the type of just unfold, actually? Use unfold R, it says these days. Okay. Yeah, see, this isn't really what I want. Because I want to be able to return... Yeah, this is totally not what I want. I don't care about the intermediate states. I want to return one value when I'm happy with the result. Oh, and I happen to find the one in data list non-empty instead of the one, whatever. It doesn't matter. It's not the function I want. So, I mean, I could just say, like, this is go of... like, 0... Because I've pressed 0 buttons. And the joltages. Right? And rather than counting up the current joltage, I can count down the goal in a way. And if I get them all to be 0 at once, then I've succeeded. Because not just the joltages, but like a set containing the states I can be in, which is the start state. There's only one of. And it's, here are the joltages. Now the joltages are a list? It would sure be nice if they were a map, wouldn't it? An int map? Okay, let's make that change, I guess. I guess I'll do it this way, actually. So we have an int map of int mapping a number, which is the counter or whatever these things are. I forget already. Are they counters? They're indicator lights, I guess. Whatever. Column voltages anyway. Take that. And then I need to fix the parser again. From list zip 0 like that. So parse some ints, zip them with 0 and call m from list on the result. That might be right. I haven't finished writing this function. Yes. And it's just warning me about stuff I'm not using or haven't finished, which is fine. Oh, let's run main one more time just to make sure I haven't messed anything up. Undefined! Okay, but that's only in part 2. That's fine. Part 1 still returned 436. Okay. Oh, you know, we don't even have to stop if any of the states are Right. No, of course we do. If a state is solved, we will immediately stop. But if a state expands to a solved state, we'll handle that at the next step. Okay. Go steps. Do I even need a 0? I could do this more recursively, right? Well, tail recursively in a well. This is kind of the tail recursive approach where I add 1 to steps. But couldn't I just say add 1 to the result of calling go on a different set and have it return 0 when it's done? I think I should do that actually. Go of states, I guess, which is a set of int sets, is so I think I want to case fold LM, which I probably have to import from somewhere. Data foldable, okay. Case fold LM. So it takes left-right fold over the elements of a structure. B, the value we're accumulating, then A, the value we actually have. Okay. The value the list item. So fold LM of children, I guess. Our initial value well, wait a minute. I don't have anything to fold. I want like map M, which is traverse. Yeah. I don't want fold LM. I want... Okay, where's traverse? Presumably data traversable, I hope? Yes. That's probably actually in Prelude these days, isn't it? Yes, it is. Okay. Traverse children of states of left. Well, it'll just be 0, won't it? It'll either be left 0 or right the next stage, right? So actually I shouldn't return a left, I should return a nothing. Okay, so this is actually going to be... just states prime 1 plus go states prime, right? So actually this is looking a lot like an unfold in a way. My seed is the states. Yeah. My seed is states. Okay, give me back the docs for unfold. I might want this after all. So if the seed were A, if I return a new seed and no, a value and maybe a new seed, it'll give me back, but I don't care about the, well, I kind of care about the list because I want to know its length. Oh, I don't know. It doesn't. I think it's easy enough to just do this myself and not try to figure out how to handle the length stuff. So I think this is fine as a structure. And this really you could write this using the maybe combinator instead of a case match. Maybe 0 is the first argument, and the second argument is call go, then add 1, right? Because go is returning an int, yeah. I don't think that would be easier to read, so I'm going to leave it as is, even though it's longer. And then we have children. Let's see. So children actually has to be... Oh, actually go also has to be a child of solution in the where clauses because it needs the machine in scope. Children of S, the state, if the state is all zeros, then we have succeeded. We have won. How do you ask an inset if it's all zeros? I mean, we could call elms and ask, is it all 0? But I guess what would make more sense is to call find max and ask, is it equal 0? Return nothing, saying there's nothing to do. We have found the answer. Immediately halt all other plans. If the minimum is less than 0, then someone has been pushed too many times. We just return nothing. We say, oh, excuse me, just an empty list. There's no solution, so the computation should continue, but not this branch of it. There are no children of this branch. Otherwise, we still have hope that this branch may lead to a solution, but we don't have a solution yet. Otherwise, it's just of 4 and where's 4 data traversable, I bet. I typed far. What's wrong with me? It is in data traversable. Is it in? No, you do have to import it. Okay. So 4 is just, it's just traverse with its arguments flipped, but that makes it convenient for writing things like when you want them in the when you want to use a lambda, basically. 4 buttons lambda b to something. So for each button, try pressing it, basically. Well, maybe I should just traverse press buttons. That actually seems pretty sick, doesn't it? Wait, why is this not just a map? Why did I think I needed traverse? I think this is just map. Because each button, when I press it, will yield a distinct state, and I want a list of those states. Yeah. And this needs to be in a where under children, because we need to close over S. Where press B is, I think, like S union with minus or something, right? Oh, except the buttons are an int set. And I have an int map. Yeah, okay, so what do we have? What do we have in sets here? I think I'm sort of like, I mean... Oh, but I don't, this is, I should be looking at int map, right? Not int set. Int map in, let's say, strict. So insertion, yeah, key value insert. So insert with, is there like an, because I want to assume the value is there. So I guess adjust is kind of what I want. I have a key, and I just want to subtract 1, basically. And if it's not there, like, I'm really sad, because it should be there. Maybe I want to call update. And if it wasn't there, I'll throw an error. Oh no, this... Yeah, I guess alter is the one that is very flexible. It's not quite alter F. It changes the value. You can insert, delete, or update. So I guess that's what I would want. Just so I can throw an error if it's not there. Because really, like, insert with is going to do all the actual work I need. Is S foldel invert? We were calling this toggle before, I guess, but it's not toggle anymore. I have a single button, and I want to update its joltage. I want to update joltages for it, I guess. Update, decrease joltage. Starting with the initial state. And B, we can just sort of leave out, right? Decrease joltage. Okay, so what order does foldel take shit in? The int is second, and the thing you're changing is first. So I guess it's state, basically. J, the joltage, is m dot alter, which takes the function first, decrease, then the key. What's the key? So I'm folding over the buttons. Okay, call this B, actually. This is like a button number, isn't it? Because press... No, this is not a button. It's a joltage index, I guess. Joltage index... state. Decrease takes a maybe and gives you back a new maybe. Decrease nothing is error. Like this should break the program. Key not found, I guess. Decrease of just I is just I minus 1. That's very simple. This might be finished. I've written all the stuff I meant to write. I probably forgot some things or did some things wrong. But let's see what the compiler thinks. It doesn't even like where. Which one? This one, surely, right? Yes. Because it is wrong. I keep thinking I have to hit enter when I'm done with that, and I don't. Another one. Wait, what's wrong with that one? That one looks okay. Otherwise equals. Okay, now we're getting to actual logical errors. We've graduated from syntax to types. Yikes. Yeah. I can think of a few problems already, but yes, this one, I've made a list of maps instead of a set of maps. That's easy enough to fix. But I also never combined all the sets that I had, I don't think. I never I produced a list of states, but I said I was going to have them take a set, and this is a list, so that's fine. We looking any better yet? It's still pretty bad. Oh, if I had a better development environment, it could warn me of this stuff as I go. But mine is all very clunky and bad and old. Okay, so what arguments is Go supposed to take? Let's give that a type. Go, I think, takes a set of... Oh, this should be... Hang on. This should be M, an int map. I wrote I because I was thinking int, but it's not an int set, it's an int map. Okay, I think this is a shorter list, probably. Oh, yeah, and traverse... So convert the list of states into... the set of states into a list to traverse it? Maybe? So I'm kind of... I don't know. The uniquifying step here is a little bit weird to me. I'm just briefly uniquifying it to make it an argument and then flattening it back into a list. I think there is probably a function in data int set, some fold, that would do something like traverse. Like mono traversable or something, maybe, has an instance here. I don't know, that doesn't seem like what I want anyway. Okay, how are we doing? Well, the error list is definitely shorter now. Oh, so wait, what is joltages? Is it already an int map? It is, it's an int map of int. So this should just be that. Singleton of joltages, right? Because we're keeping a set of int maps, and that's what this would be, a set of int maps. I want the foldable to list, but okay, we'll use Wait a minute. The type for this is wrong. I was thinking, okay, I need to put types on some of these things because it's inferring types I do not like, I think. Go is a function from a set of int map to int, right? All int map represents the joltage goal remaining, and I have a set of them, the states I'm currently exploring, and the result is an int. Good. So, how about children? Children should be... Well, first of all, this I guess I can use s2list. A function from... Calling this an S, because it's a state, I guess. But it's actually a map, an int map. Int map int to maybe list of int map int, right? Okay, let's see if that makes things any better. Okay, this is obviously crazy. It should be in map of int. Okay, we have much smaller errors now. I wouldn't say there are a few of them, but they're smaller. What is this saying? Let's leave that one for a moment. Ah, yes, and because I called it S, I got confused and thought I should call S find max on it. But actually it's an int map. I should call M find max on it. How are we doing now? Just 2 errors left. Okay, still gonna leave the first one for a moment. I have a set of int. Oh, the buttons, I'm calling map on it, but it's not a list. Oh, it is. It's a list of int set. Well, this is what I wanted, so maybe it's inferred the wrong type for press. Press, I think, should have type button to int map int. So it's now saying, yeah, if your function had that type, I would be happy. Everything that calls it uses it at that type, but it doesn't have that type. You have a set of int, but you should have an int set. I think. Ah, this should be... No. What? Like, yeah, I think it is saying you have a set of int, and you need an int set. I don't know quite where it's getting the set of int from, is what's bothering me. Oh, well, B is an int set. I'm calling sfoldel, and it's saying, oh, you must have a set of ints somewhere. But I don't. I have an int set, so I should use ifoldel. That's what it was upset about. Okay, and now we're just down to this last error. What's this all about? Or this first error, I suppose. So states prime, it thought would be a list of int map, but actually it's a list of int map. That's true. Traverse is map m. Okay, fine. There's probably a better way to do this, but I'll call concat of states. Oh no, I made it worse. Alright, put it back. That was probably the right change to make. Oh, I don't know. Why is it that if I fix this error, suddenly everything else breaks? I guess because now it's going to infer a different type for something else? No, because I gave it types for children and states. Oh, is it supposed to be here? Yes, this was the one. No instance. I have a pair of key and int that was supposed to be as. Oh, yeah. In int maps. Min and max. Look at min, find min. I see. These return to me a key and a value, but I don't care about the key. No. Oh, also look up min is the wrong fucking thing to do anyway. Because it's going to look up the minimal value. Thank goodness this didn't type check. I might not have noticed my mistake if it had just... Okay. Alright, so I'll look at all the values and check whether they're all 0. Here. So these should both be errors, right? Why is only one of them an error? That kind of puzzles me. So if the biggest value in the map is 0, I have to be careful. These are in the wrong order. Because if any of them are negative, but the maximum is 0, that doesn't mean I've succeeded. It means I've failed. So I have to check this first. So if the minimum element is less than 0, we prune this branch. Otherwise, if the maximum is 0, then they must all be 0. And if none of that is true, then we continue working. And M is int map here. Okay. So this compiles now. A nice change. Let's try running it. I mean, how bad could it be? It could be slow. Hopefully not too slow. Because I am pruning the search space. But I'm not exploring it in a very efficient order. Well, let's look at the inputs here. I mean, I guess this is kind of a big search space, huh? There are 10 buttons. Ish. And I have to make at least 100 presses for this last one, for example. I have to make at least 105 presses. Probably more. And the search space won't actually get trimmed until we've pressed like this button 29 times at the earliest, right? So we'll be exploring something like 10 to the 29 options. That's a few too many, I think. Oh no. Okay, so this is obviously never going to complete. I didn't think that through. But I mean, would A star be that much better? I don't think it would. Right, I would start exploring towards, I mean, I would be first pressing the button that, all the buttons that cause this to go down, because that's the furthest, the way I could get, my heuristic could be improved most quickly, because my heuristic is related to the smallest, the largest number. But there'd still be at least 29 steps. Like where, okay, where do I see 0 in this list? 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 different ways to toggle button 0. And the earliest way any of them could get pruned would be if one of them also toggled button 4, which one of them does, this one here. But even then, it would only be toggled after 29 steps. But I don't actually have like 9 to the 29 possible states, right? Because pressing button 0 and then button 5, the one I'm looking at now, is the same as pressing button 5 and then button 0. They would have the same state and be at the same depth. So those would get trimmed into just one state. So we'd kind of be exploring instead, like, the number of ways... How many zeros did I say? Oh, I'm looking at the wrong... The zeros are down. They're not even on that upper line. 1, 2, 3, 4, 5... 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, there are 9 zeros. And how many of them can touch button 4? This one's second from the... Yeah, so this one and this one. But we'd be looking at something like at least 29 buttons chosen from among 9 options. And this is like a stars and bars kind of problem, I think. But I'm pretty sure the number is still large. How many ways can you distribute 29 items between 9 things, basically? We would have at least that many states going, and in practice, many more. Yeah, split 29 things between 9 categories. There's a lot of ways to do that. And in practice, it would be more. So that's not really going to work. I don't think A star would help. So is there a smarter idea altogether? Well, I guess just to entertain myself, I'll try, we'll just see if my solution is at least correct, even if it's too slow to run. Oh, whoops. No, you tricked me, Emacs. The test input for today, please. This is a problem with the I do file selection mode, which I love, but every so often it has this one quirk that, like, if you type in a file name that doesn't exist here but does exist somewhere else and you're not fast enough, it replaces it with the one that exists somewhere else. 7 and 33. Yeah, I mean, 33 is right. This is a correct algorithm. It's just too slow. So how could you do this more efficiently? I mean, there was this idea I had before about, well, let's see. Like, looking at this second state, we can see we have to press button 2 at least 5 more times. Sorry. We have to increase joltage to light number 2 at least 5 more times than we do anything else. So we could say, all right, well, the first 5 button presses can't include this one, right? So we could choose 5 ways to press a button that isn't this. And there would be a number of ways to do that. But each of those would presumably have a new, like, highest number. And we could say, okay, well, if I've done this, now I have to press that button at least n times, right? Like, for example, suppose I said, okay, I need to press the button, I need to toggle this light at least 5 more times than the others. I'll try doing that by toggling this light 5 times. Well, I would 0, 2, 3, 4, so we toggle everything but this. So this would be 2, 5, 7. I don't know. Then I could say, oh, well, geez, this is still the highest one. I have to press it at least 2 more times before I can get to this guy. But this would immediately be an error. I would say, well, this is impossible. Because the one labeled 4, I've pressed too many times. So, I don't know. Like, you could... Maybe there's some give and take between things you have to press a lot and things you have to press very rarely. Or maybe the opposite? Because here I can see that button 4, light 4 can only be toggled twice, total. So maybe what I do is from among the buttons that touch light number 4, I choose 2 of them to press. Maybe the first one twice, maybe the first one once and maybe button 0 once and button 2 once, something like that. And then for each of those, I update my state of lights, but then throw away all the buttons that can change 4 because it's illegal to press them again. I feel like this isn't actually improving things, though, because it's... I think it's just changing the order I explore things in. I don't think it's actually trimming things down. There's another technique you use in like a the change-making problem, where you you do it kind of broken down by denomination. You commit, like when you're saying, oh, I need to make change for 28 cents. How many ways can I do it? Well, you can either give them a quarter now, and then make change for 3 cents, or you can say, I'm never going to give them a quarter, and then find a way to make change for 28 cents that involves no quarters. right? So we could do the same here. We could say, all right, am I going to push this first button or not? If so, then start a sub-search where we've pushed the first button once. And otherwise, start a sub-search where we don't push the first button at all. With a smaller list of buttons. I'm not sure that really helps. Again, I think it kind of just changes the order I explore states in. And one advantage of exploring them depth first is that when I find a solution, it's guaranteed to be the best solution. If I explore them in some other order, that's no longer true. All right. I mean, I've been at this for a while. I'm going to go take a break, think about this, maybe come up with an answer. Maybe I won't be back for a few million years, and by then Emacs will have completed, although I think it would take much longer than that. Back in a bit. All right, I'm back. It's like 24 hours later, maybe more. Less? Less, I think. But close. I had some time to think over the problem, which... It's been 24 hours for me. What was the problem again? The problem was that my solution, while correct, is searching a very large graph in a not nearly efficient enough way, and it would not have finished before the sun burned out, I think. So, I didn't even let it run overnight. I was that confident that probably the sun won't burn out overnight. So... I thought some more about how would you, like, what would be an efficient way to solve this problem, and I realized that this is a system of linear equations in integers, right? We're saying that the number of presses of whatever variables, whatever buttons touch light 3, those add up to 3. The ones that touch 5, the touch number, light number 1, those add up to 5. The ones that touch light number 2 add up to 4. Right? So we have a system of 6 variables and 4 unknowns in integers, positive integers even. I remembered from a previous year of Advent of Code, I think it was last year, but maybe it was 2 years ago, that like there was at least one day where like solving a system of Diophantine equations, I think that's how you say it, which is like equations where only integer values are relevant. You don't accept irrational. It was like there were only 2 variables though. It was, I remember you had to like, you could either do A or B, and each of them increased some, like, I don't remember exactly, but like each A and B increased some other numbers, you know, y1 and y2, I don't remember what they were, each by a different amount. So like button A maybe increased y1 by 5 and y2 by 1. Something like that. And B increased them by different amounts. And you had to find the minimum number of presses of A and B that would get you to the goal values of y1 and y2. y0 and y1, whatever I called them. And that's very much like today, except that we have 6 buttons instead of 2. And indeed a variable number of buttons. And a number of goals, which is not just 2 either. And so I don't remember what I did that previous year. I think I did like a long binge on Wikipedia and read about like solving Diophantine equations and computing the GCD, which you have to do to like try all the solutions. But I was like, I don't want to do that again this year, especially because like solving a big system of them kind of sucks. You have like you have 4 equations, and like you can solve equation 1 in terms of one of the variables, then substitute that into equation 2 to get a new equation that mentions one fewer variable, and so on. But you have to be like careful to pick the right variable, because what if, I don't know. It just didn't seem like a lot of fun. And so I was pretty close to just having this video be, I'm not going to do part 2 today, right? I'm doing this for fun. It didn't seem like fun to do a bunch of algebra. And it was going to be a lot of work in a video that was already 3 hours long. But then I remembered, well, okay, first of all, before that, I was like, well, what about, I remember last year I looked at this, I searched for diaphantine on Google, and all I found was this, like, library that is mostly about some alternative concept of algebras that I don't understand, but also has, like, GCD and diaphantine functions in it. And you can, like, there is this diaphantine multi where you could give it a goal and a single equation, and it'll give you back maybe, like, these are the coefficients of your linear equation. And it would give you back a solution if it could find one. And it's a big hassle to use this, but you can. And I think you can combine this with Chinese remainder multi to do the substitution back in some way that I don't remember the details of. But it's just like, I didn't want to do this. But before I decided to give up, I was like, well, okay, let's look again for, maybe there's something in Haskell for solving linear equations in general, not specifically diaphantine ones. And what I found was math.linear equation solver, which evidently what it does is it, like, delegates to an SMT solver, which I guess is different from a SAT solver. I don't know the details of how that works. SAT solvers are more about Booleans, and I guess SMT maybe is enriched to understand ints. I don't know. And it supports delegating to a bunch of these, which it turns out you have to have it installed on your system, and it shells out, like, to the actual executable, which surprised me. It took me like 15 minutes for GHC to build all the dependencies this crazy thing has, and then it was still like, oh, Z3 isn't on your system. So I had to go apt install Z3, but then it works. So, and it has a nice, simple, you say, tell it what solver to use, a coefficient matrix and a result vector, and it tells you, okay, here's a solution. And I don't quite, it gives you all solutions. So how does this, maximum number to return in case there are infinite, I see. So I don't know what order it gives them in, but hopefully it doesn't choose negative numbers if it doesn't have to. Because if, in principle, there are probably an infinite number of solutions to a number of these that involve negative button presses. Right? Where, like, obviously that's not permissible as a real solution to our actual problem, but would be to this linear equation. And then they have rational versions, which we don't care about. And I have tested that I can call this thing, and this is an example from their docs. It's not something from Advent of Code. And it gives me a number. So I'm going to try using, let's get rid of this numeric prelude dependency. I'm going to try using this linear equation solver. It'll be a nice way to enrich myself to, like, interact with a SAT solver, or SMT solver, I guess, at least a little bit, even if I'm basically just doing it through some wrapper. So I want, though, to do a few things first. Don't add that. And I just want to commit what I have, because it's correct but not efficient enough, basically. And I think that's interesting. Actually, adding this didn't seem to do anything. I don't really understand. I still don't understand how stack and cabal interact. It seemed like when I added this, it still said, sorry, I can't compile your thing. But then when I added it to the Cabal file, it worked. So I don't know. Day 10, part 2 solution that is correct, but unfeasibly slow. So this way, I can at least have this, in my pocket if I decide to give up on... And I'll have a solution that is technically correct. But not actually useful. Because this was fun and interesting to write. It just isn't good enough. So I want to leave some record of it in the Git history. But then I'm going to tear it apart here. So solution is still a function from machine to int, but it's just going to be a call to the equation solver, I hope. Well, maybe I should do a little bit more first. Maybe I should run the test, their example input by hand before I write something that. So here's their thing, and I'm thinking, let's say solve linear. What? Oh, integer linear equals. Let's just ask for 1. Okay, and its type is, it wants the coefficients and then the results. So we have 6 variables. God, this is a long... Okay, so how many... We have to first see which ones affect button 0 and say that those add up to 3. So the first one does. Second one doesn't. Does. Then how many of them affect button 1? No, yes, no, yes. Which ones affect button 2? No, yes. Oops. No, yes, no. And lastly, button 3, yes, no, yes, no. So those are our coefficients, and the goals are 3, 5, 4, 7. I have to tell it what solver I want, which is SMT. It's not SMT, it's Z3. Okay, and it says you could do this with 9 button presses. I don't think it was such a large number, was it? It says you could do this with 7, actually. Pressing button... Oh no, I'm reading the part 1. Okay. I was reading part 1 answers. Well, this is bad news. Configuring the first machine's counters requires a minimum of 10 button presses. What did I... Oh, I typed 2456. It should be 2457. Yeah, and it says, oh, you could just do a negative number of presses. Great. Give me 10 solutions, please. Oh. In this order? Yeah. So these all have negative numbers in them. I don't know how I'm supposed to ask for only positive numbers. And even if I said, hey, you know, give me like 20 of them, maybe one of these in here has no negative numbers. I don't know. But even if it does, I can't really be sure that it's the minimal solution. Okay. Let's go look at the docs a bit more. I don't think there's actually going to be anything here. Yeah. So probably you could, like, if you use the SMT solver directly, you could specify that the numbers have to be positive. But if all we have is equations and not inequalities, I can't add another inequality that says, like, each button press must be at least 0. I mean, we can go look at Z3, but... Oh, right, this just refers to... Yeah. So I don't think I can use this interface to get an answer. Because there's no way for me to say you can't press a button negative times. Is there some clever thing I could do that's equivalent to that? Like... I don't think so. Well, I guess in some sense I could. Because I could add one more equation. No, that still wouldn't help. I was thinking, I mean, maybe it would help. What I imagined was, okay, well, I know for this one that the actual goal number is, what is it, 9 or something? $10. I could then say, also, there's another goal, which is affected by any button that you press, and it has to add up to 10. And this still doesn't fix the problem because, like, pressing button 1 3 times and button 2 minus 2 times is the same as pressing them in total once. But maybe it constrains the problem enough to get me back to one solution. Nope. Gives me a bunch of solutions still. Although, the last one has only positive numbers. the last one, really. 131302, and that is 10 button presses, so that idea worked. Right? And like, if I asked for like 22, I'm asking for exactly 22 button presses. Oh, no, I'm not. Right, sorry, excuse me. But if I put like a 22 here, I'm asking for exactly 22 button presses. And it says you just can't do that. But with negative numbers, you could. So what I might be able to do is try an iterative approach where I say, hey, can I do this with one button press? And look for only positive numbers, positive answers. Then say, could I do it with only 2 button presses? And the first time I get an answer back where all the buttons are positive, then I say, we did it. The problem is all of these are underspecified, and so like how many solutions do I need to ask for to make sure I get only positive ones? I don't know. 100? Maybe. So it seems like this could be an approach that might work. Right? Maybe. One problem, I suppose, is that this function does I/O. It actually calls Z3 as a separate program. So I can't... I'll have to slightly change... oops. I'll have to change part 1 to just return I/O, and I'll change my main accordingly, which is fine. But I think it's worth giving it a try. Hopefully it's not too difficult. And if it gives us answers, wouldn't that be nice? Now, is there some way I can predict how many solutions I'll have to ask for? I don't think so. But I can, I suppose, like, I can put an upper bound on the number of buttons I might need to press and only search that high before I declare defeat. And then if I get defeat, I can go back and ask for a bigger number of answers, I suppose. I don't know. I mean, it's worth a try, I guess. So this is an I/O event. And now we're gonna have to do a different main. Input main is do. Input is this. Print. One input. Like that, because part 2 has to do I/O. Let's see, how can I quickly test that this, I mean, I guess I can just say undefined, right? Yeah, and this compiles. So this is the right main. We just need part 2 to actually be implemented. So What, so it's like, I want to traverse fmap sum traverse solution. So solution is a function from machine to IO of int. We're traversing, which is map-emming, over the list of machines, getting back a list of... Well, the map gives us a list of IO int. The traverse gives us an IO of list of int, and fmap sum reaches into the IO and adds up. Yeah, that seems right. Okay, so machine is a function returns IO int. Yeah, so this all type checks. Great. Let's just start a do right now. We don't necessarily need it, but why not? So we need... What are my buttons and joltages? Joltage, they're both... Okay, so the joltage is an int map of int, which... And the button is a list of int sets, so its length will be the number of coefficients, because that's how many buttons there are. Yeah, okay. Let's see. Let coefs and what do they call the thing on the right? Results, apparently. Okay. The unzip of why do I need to... So I have a list of buttons. And a list of joltages, which are of different lengths. I guess I have buttons and joltages separately. There's no need to unzip them, right? I don't know why I thought there would be. Well, do I still have 4? I don't. I took it out again. So for each button, button is an int set. And each one, they correspond to, okay, num results length joltages. So it's not actually length, it's I size because InMap... Oh, InMap is foldable. Okay, so length should actually work and be efficient. I guess... Oh, my brain is kind of burned out on this problem. I guess I want to iterate over a list of all the joltage indexes, right? Fine. I for some reason I wanted to avoid writing this multiple times, but whatever. Yeah, see, this should just be a do. I should... So for each button, I'm returning an entire equation. So I have to call pure, but then I do because I want another... Yeah, see, I don't know. Maybe this would be better with 4. I can't decide. R from this, I guess. Pure of if. What order does int set take its arguments in? It should take the key first, right? Yeah. If r s member of B, the button, then actually just get this on one line. So it's either 0 or 1, depending on whether R is a member of B. I'm going to have to import this. So bool is a function that you give it a false value and a true value and a Boolean, and it gives you back the appropriate value. It's the same thing as if, but like just syntactically different. It's just an ordinary function instead of having syntax, and it's convenient to fit on one line. And it emphasizes here that we're using bool 0, 1. It's like we're getting either 0 or 1 as a result of something here. So I think that's probably legal. So does this all still compile? Okay, what the hell are my types? Oh, int set is I forgot. Yes, this all type checks. Great. But I guess I haven't used coef, so it might be the wrong type. Results is just elms of joltages, right? Yeah. So I guess I'm ready to call... Well, right. But the problem is... if I wanted to just call the solver here, I could. But the problem is, we determined that I don't know how many results I have to ask. Like, I have to over-specify. I have to over-specify by saying I need the number of total button presses to be n, where n is my goal. So I have to like start at 1, basically. Ask, hey, can you solve it for 1 with only positive numbers? Can you solve it for 2 with only positive numbers? It's kind of annoying to be in I/O for all of this, because not all the list tools work as easily as they usually would. I could, for example, produce an infinite list of I/O actions. Maybe I'll just do that. No, I don't want to look at that file. I want to look at this one. So, like, there shouldn't be more than... Well, there's at most 10 buttons, or 10 lights, I think. And none of them are getting pressed more than 100 times, I'm reasonably sure. I don't know. We do see some big joltage numbers here, but like, often these are, like, yeah, there's a bunch of buttons, so every button I press is going to contribute like 4 to the total or something. So the total number of... Okay, that's a question. Like, how many total joltage do we need in this? I mean, it's about 10 times 200. It's not really. It's more like 8 times 200. 1600. But I guess we could actually determine programmatically for a specific light what the maximum number of buttons we could plausibly need to press is, right? And it's the sum of joltages divided by the maximum number of lights, the minimum number of lights affected by a single button, right? On this list, the most total joltage you can possibly get, or the least joltage you can get by pressing 1 button, is 3. So I don't know what this all adds up to. Let's say it's 1800. Then we definitely need at most 600 button presses, right? Because we could be pressing this one 600 times, and that would obviously not be the answer. But that's the most button presses we could spend without getting too high a joltage. So if we've pressed 600 buttons, our joltage is at least the total, right, is the idea. So I could just say 600, but it's kind of nice, actually, I think, to compute it for each problem, I guess. So we don't have to go overboard on all of them. Max presses needed is sum of joltages divided rounding down, I guess. Like, in principle, this should round up, but this is just a gross estimate. It'll never be as high as this. Divided by minimum of map I size of buttons, right? That is a number. And since it type checked, it must be what I meant. It's hard to imagine you could write this, have it not type check, have it type check and have it be wrong. So now we have the max presses needed, and we can basically just say like attempts is do. No, because it's gonna have to be an IO, isn't it? No, I can produce a list of IO actions, not perform them all, and then iterate through that list, performing them later. So let's do that. Total presses comes from 1 to max presses needed. What's the solve function? It's called solve integer linear equals all. And we need one more. Oh, I guess what we can do is say extra coef is 1 mapped over voltages. No, over buttons. So each button, count each button press. Okay, and what arguments order does this take? It wants C3 first, which we haven't even imported yet, but whatever. And let's say we want 100 answers. Then our coefs is so add this extra constraint. No, wait. This is not, okay, this is an extra equation, right? Right, and that's right, because I only want, this is never going to change. All that's going to change is, okay, coefs prime, and then total presses const onto results, right? Well, I guess weirdly I can just do this, right? Yeah, okay. Sovel? I don't think it's called Sovel. No, this isn't right. So I want to return one item of a list. And that item is the result of fmapping into an IO action. And what I want to fmap is the result of filtering that it's greater than 0. I guess. This type check. No, for numerous reasons. This variable name I changed. Z3 and solve aren't in scope. Well, that's easy enough to fix. What is the name of this package? Math linear equation solver. Z3 solve. What is this fucking function called? Yeah, I always get the order wrong. Solve integer linear equals all. Okay, apparently I'm not allowed to just I have to import the type. Fine. It wants integers? Or it does. It demands integers. It won't take ints. Oh, and I guess that other error is... No, it's saying this actually doesn't type check, not just it's not the result type I said I would use. Because I'm still just saying pure 1. So this computation is being thrown away. Okay. Kind of annoying that I have int sets, which are specific to int, and then I need integers. So my coefs... Length returns an integer shortly, right? I mean an int, rather. It does. So we need to convert that to an int. Do I? Yeah. Because I'm saying from 0 up to... Okay. From integral? Is that the type I'm looking for? Yeah. Kind of crazy to have to work with integers, but okay. So 1 over buttons, that should solve itself. And this 0 and 1 will also be interpreted as integers as needed. Actually, wait a minute. Maybe this isn't necessary here, because R is just going to be... Oh no, actually, I do need this to be... R has to be an int, because I'm using it to look up in an int set. And then this should be polymorphic. Sorry, not this. This. These 0 and 1 are polymorphic. So that should be fine. Here, though, the elms of the joltages are ints, so I have to make them integers. And the max presses needed is going to be looking at a bunch of ints, so this also needs to be from integraled. What do we think about this? Closer. All the int problems are gone, and now it's just saying you're f-mapping over something which... What are you up? Solve interlinear equals all. Should be an IO. Oh. It's an IO of maybe list of int. Or no. It's an IO of list of int? I see, because I'm getting... Well, we're f-mapping into it. So I need a function from list of int to list of int. Right? And I want to filter that they're all positive. That seems right. Fmap is applied to... Oh. Yes, I see. You're telling me this parenthesis should be over here. Okay, that all type checks. Is it right? I mean, who could say? And then I think I want to basically write a function that loops over the list of attempts and returns an int. So I kind of want to just say, like, find first of tries equals just say that for now. So if we have an attempt left to try, we have to first do the IO in it. You know, it's probably simpler if I just do this. Just give me all the solutions, and then here I'll look at them and filter the ones that are because now I'm working with a try value that isn't wrapped in IO anymore, and that's sort of nice. Filter all greater than or equal to 0 of try. well, I don't even need this to have a name, right? Case filter the positive solutions from the trie of, if it's empty, there are no positive only solutions, then we just say find first of the remaining attempts. If there is at least one solution, then, and I guess I don't care if there are any more. I think I can just add up the solution, right? Because it's going to return a list of coefficients that solve the solution, and my coefficients are how many times each button was pressed. So I think I can just say pure of sum of sol, right? So this do, it turns out, didn't ever need anything. It's just a bunch of lets. In find first attempts. It's a bunch of int. Okay, fine. You are permitted to return an integer. I'm not going to come. It's fine, whatever. Oh, I gave this a type. Well, I guess at that point, I'll just have it be an actual int. So add up the solution, convert it to an int, and then return it. It type checks. I mean, we don't know if it's right yet. Received ill-formed input? What do you even mean? Ill-formed? Okay. Well, the good news is I'm in I/O here, so I can just do some actual printing. Print of this? Like, what is it that you're so upset about? Yeah, that doesn't look right. Okay, my extra coefficients list is the wrong size. So it shouldn't be the length of the joltages. It should be the length... No, what? It should be... Yeah, the length of the number of... This does not look well formed, aren't there? I think there are supposed to be 6 entries. Not right. Like each equation is supposed to have 6 variables. Yeah, I think one of my matrices is sideways. There's supposed to be 4 equations in 6 unknowns, not 6 equations in 4 unknowns. Maybe this is why I thought I needed to zip something. Because, like, okay, light number 0 needs to have a total... Sorry, this is light number 0. The 1 is the artificial one I added in. Also, its number is ridiculous. This shouldn't be... Oh, no, this being 1 makes sense. I'm saying, oh, is there a way to solve this by pressing just 1 button? There's not. And then I'll try it again with 2. But 3... All right, what's the test input I'm actually running on here? So here what I should be saying is that the sum of x0, x1, and x3 should be 3. So there should be 6 variables in each equation. That's correct. And I bet if I look at my thing, it'll be like... Well, I was going to say I bet it's transposed, but it doesn't seem that that's true. Oh, yeah, it is. Oh, and I was wrong. For light 0, it should be buttons 4 and 5. So if you read down this column, 0, 0, 0, 0, 1, 1, this is correct but transposed. Okay, so rather than like fixing the problem in the appropriate way, I will just put a transpose in there. There's not actually a... And if... So I should be... I guess the point is I should be iterating over the joltages first, right? Maybe that's all that's wrong, is I just need this. And then I get things in the right order. Yeah. I think 33 was the right answer, as I recall, right? Yeah. So, I mean, this is slow. But not outrageously slow. I mean, I might just be able to run this. I'll leave the printing in, why not? So what happens if I just say stack run? Yeah, I mean, it looks like it's churning through the numbers and getting answers. Not erroring. So I think this will return in a reasonable amount of time. Boy, this one's slow. Because there's so many buttons? Now, one thing we could try to speed this up, maybe, would be a kind of, what's the word for what I'm thinking of? Like binary search on the solution count, where like instead of trying 1 and then 2 and then 3, when like those are obviously never going to work, we could try 1, then 2, then 4, then 8, then 16, and so on until we get at least one solution. Oh, but that won't work because I'm saying there's exactly one. I'm requiring the specific number of button presses. So there won't be any that require like, whatever, 256. Okay. So I think this is kind of just fine to run on its own. I'm not going to interrupt it to take the printing out. Because printing doesn't seem to be the bottleneck, right? The actual solver calls are the slow part. It would be nice if it printed, like, something better. Like, if for each... If it just printed out the number of the machine that it's working on, so you can see how close it is to being done, and if that were all it printed. But I mean, I can't so easily add that to the framework that I have here because the iteration over the list of machines is handled for me by traverse. I could traverse over, like, zipping the solution, zipping with 0, maybe? Maybe that's fine. Print. Did I even... This. So I could do this basically. So I'm not going to interrupt it. Oh no, an error. Okay, great. Well, great. Okay. So I'm going to assume it would have figured this out, but there were just too many solutions, presumably, right? So I think what I'll actually do is instead of 100 here, I'll say, give me total presses, total solutions, so that, like, the more... Well, that's probably okay. Times 2. No good reason. But we saw in some of our tests, playing around at the beginning, that, like, you know, there were 10 there were 10 maximum total joltage required. And I asked for 10 solutions and didn't get one, but then I asked for 20 and did. So maybe that's related. Yeah, of course I have to. Of course, this one wants to be. Oh no, this one. Okay, a bunch of things went wrong here. Oh, solution. Okay, that's true. Well, uncurry the solution, why not? So solution can still take a reasonable. Okay, but like... total presses. Oh, the issue is that total presses is being used in a context where it's supposed to be an int and a context where it's supposed to be an integer, and it picked one of them to be right. Intral? Wow, I missed multiple keys in there. And I typed one of them wrong. Oh my gosh, I must be under a great deal of stress. Okay. So this way we can at least see which machine it... Why did it print 436? Oh, that was the part 1 solution. I see. We can see which machine it broke on, if it indeed still breaks. So, okay, I'm gonna pause the recording here, and I'll let this run until something cool happens. All right, I'm back just to put a cap on this one. I'm not gonna finish this video, or well, I guess the video is by definition being finished. I'm not finishing this puzzle. I believe I left you when... Oh, there's all kinds of junk on the screen that I have to explain. When it was... I had come up with this way to, like, say, okay, there was this function that uses Z3 to solve linear integer equations, but it didn't have a way to limit them to be positive solutions. So I tried a little fix where I said, oh, they all have to add up to the total number. Like, I started looking for... I said, give me 20 solutions, and I like hoped that one of them would be all positive. And I also said, by the way, the total number of presses has to be like 1. And then I said, oh, well, actually it has to be 10. It has to be 20. Like, and I just cycled through. And so this worked on some of the inputs, but it took a long time on some of them, and it like failed on input number 8 out of 156. So I added some more instrumentation and tried a few new ideas. Like for optimization, I realized that I had computed max presses needed as like, you know, the total amount of energy needed at the end divided by the minimum amount of energy you can put in at a time. I hadn't thought about, at the time, a minimum number of presses needed, which is just like, well, you can only, each button only increases each joltage by 1, so whatever joltage is the highest, you need at least that many presses. So I added that to trim the search space. I added more instrumentation to print how far it was going, you know, its progress, and it never worked. It didn't get any further than 8, which took like 15 minutes or something. So I tried one more thing, which I did off camera because I didn't want to do a whole nother investigation of an API on camera. But I looked into using Z3 at a lower level, rather than using it through this library that's designed for solving linear equations. And it turns out Z3 does have, you can say, oh yeah, you can put inequalities into Z3. There just isn't support for it in the Haskell library that uses Z3 to solve systems of linear equations. Which is fair enough, because these are inequalities, not equations. But the Z3 input file format is pretty simple. And this is kind of a pain to write, but you could write it. You could write a Haskell program that outputs this for each machine. And, you know, the input that it gives you back, the output it gives you back is this. It says, yep, I was able to solve it, and here are some definitions that I used for all the variables you gave me. And I could parse this, and it gives the right answer, 10, for the test input. But I did not want to do that. It's just a lot of, I don't know, I mean, like, I've written parsers for Lisps before. This would not be a hard parser to write. but it would be a bunch more work, and I just want to get on with my life. I also looked into... Because, like, normally when you're writing a program to interact with Z3, it shouldn't be through text. Z3 has, like, bindings for C and Java and Python and JavaScript and some other things. And someone's written a Haskell library that wraps the Z3 bindings for C++, I think, into Haskell. Maybe they're the C bindings, I don't know. But it would be I think harder than writing a parser for this to interact with that library. You know, it's written in a nice way, you know, but like it's a lot of work to do things programmatically rather than output some text for a simple case like this. And so I decided I'm just not going to do it. I found two ways that are, well, one way that's correct but way too slow. One way that's theoretically correct, except I can't limit Z3. I can't quite describe the problem to Z3 using the linear equation library. And then I found another way of, like, it would be interesting to learn to work with Z3, but I don't want to do that now that I'm, like, I don't even know how long this video. It's almost 5 hours, probably. It's got to be my longest video ever. So I'm just going to declare defeat on this problem and get on with day 11. That's life. Hope you guys found this interesting nonetheless. Thanks for watching, and I'll see you next time.